Hello students, in this video we will discuss the electric field due to infinite plane sheet. Suppose this is infinite plane sheet and this plane sheet contains positive charge on both the sides. Then to prove the electric field we have to consider a circular surface on this plane sheet, and if we consider a circular surface on the plane sheet, then due to the circular surface the Gaussian surface will be in the form of cylinder. So this is Gaussian surface. This Gaussian surface is created due to this phase, and on the left hand side the Gaussian surface is created. This is also Gaussian surface. It is created due to the charge on the sheet on left hand side. And if the surface charge density for this phase, surface charge density is sigma, then what will happen? If we want the total charge, then we have to use this surface charge density, and this surface charge density I explained you in my previous videos. Now there are three in case of cylinder, there are cylindrical Gaussian surface, there is always three phases. First phase, if we consider first phase, let's start with the phase on the left hand side. This first phase, this is first surface, remember previous proof, and this curved is the second phase, and again this is third surface of this cylindrical Gaussian surface. Now if we consider this point, the electric field at this point, what will be the direction of electric field at this point? It will be naturally away from the positive charge. So the electric field intensity will be towards normal to this phase. This is left hand side phase of the Gaussian surface, Gaussian cylindrical surface, and this is normal to the phase, and let the area of this phase is dA. So in vector form we can write it as vector dA. Vector dA is the area vector and vector E is the electric field intensity at this phase. Now if we consider the curved surface, means at this point, suppose at this point if we want the direction of E, then the direction of E will be away from the positive charge on the right hand side face of the sheet, of the plane sheet. So this will be away from the sheet, and what will be the area vector? Area vector will be perpendicular to this, so it will be vector dA. The angle between this vector E and vector dA is 90 degree. Here theta is 0 degree. And if we consider this third surface is the second phase, the right hand side phase of the Gaussian surface, and the direction of electric field intensity will be away from this positive charge, so it will be towards right hand side, and the direction of area vector will also be normal to this phase. Here the direction of area vector was normal to this phase, phase number 1, and this phase number 2, it will be normal to this phase. So we can say that vector E and dA are in the same direction, means parallel to each other. So for them theta will be 0 degree. This theta will be 0 degree for the cylindrical faces, and for the cylindrical surface the theta will be 90 degree. This theta will be 90 degree for the cylindrical surface. This we have to take into consideration. Now the total flux, if we ask to calculate the total flux, it will be represented by phi. Integral of phase number 1, surface number 1, vector E dot vector dA, plus integral of surface number 2, vector E dot vector dA, plus integral of surface 3, vector E dot vector dA. Now this is the vector form of the flux created due to different type of surfaces. Now as it was done in previous proof, it will be dA cos theta, means will transform from the vector form. It will be E dA cos theta, and the third surface, integral of third surface, E dA cos theta. Now for first surface we know theta is equal to 0 degree, so phi will be E dA cos 0 degree. For second surface we are considering the curved surface of this cylindrical Gaussian surface, so it will be E dA cos 90 degree, and the third surface is the second face of the cylinder, so it will be E dA cos 0 degree because it is 0 degree. Now we know the value of cos 0 is 1, so it will be E dA plus value of cos 90 is 0, so middle term means for the curved surface it will be, the flux will be 0. The flux created due to this curved surface of the Gaussian cylindrical surface will be 0 because of angle between vector E and area vector is 90 degree. And again for the face it will be E dA. We can add these two because the area of this face and this face are same, so we can write it as phi is equal to 2 times of E dA, and we know that E is constant if we take E outside, so it will be phi is equal to 2E integral of dA. Integral of dA means the total area. This is dA, this is dA, and if we want the total area of the plate to be considered for the electric field due to infinite plane sheet, then for the total area, the integral of small dA area of the sheet will be in the form of phi is equal to 2 in place of integral of, this is because the integral of various small areas will be equal to the total area, so it will be phi is equal to 2EA, and we know that phi is equal to Q upon epsilon naught. According to Gauss law, we can put Q upon epsilon naught in place of phi, it will be 2EA. This is the first equation. Now this A is the charge enclosed in the area, means in this area the charge will be enclosed in the plate. Now we know that Q is equal to sigma A. Sigma is the surface charge density, and when it is multiplied to the whole area of the plate, then the total charge on the plate will be represented by Q. So Q is equal to sigma into A. So in first equation we can put this in equation 1. So what we'll get in place of Q, we'll put sigma A. So it will be sigma A upon epsilon naught is equal to 2EA. AA will get cancelled. So E will be equal to sigma upon 2 epsilon naught, and this proof. Now the third application of the Gauss law is electric field due to a charged conducting sphere. Suppose this is a charged conducting sphere having radius as capital R, and due to this charged conducting sphere the Gaussian surface is created, and I told you in my previous video that the point charge as well as the charge contained by a sphere or shell, for both these the Gaussian surface is always in the form of a sphere. So this will be the Gaussian surface created by this conducting sphere. This is Gaussian surface, and suppose the distance of this, or we can say that the radius of this Gaussian surface sphere is smaller. Then if we want the electric field intensity at this point, means on the surface of the Gaussian surface, then at this point, due to this positive charge, the direction of electric field will be away from this. This will be vector E. And if we consider the small area here, then the area vector is represented by vector dA. In this way, if we talk about the electric field outside the sphere, outside the sphere means the radius of sphere is capital R, and if we want the electric field outside, anywhere outside, and we are considering a point on the Gaussian surface which is outside this sphere, and the distance of this point from the center of the sphere is small r, so electric field is represented by k q upon r square. This is electric field intensity outside the sphere, outside the charged sphere. This is outside. So we can write it as E outside is equal to kq upon r square, where k is 1 upon 4 pi epsilon naught for the free space, and this is 9 into 10 to power 9. We all know this. So k outside will be, E outside will be E outside is equal to kq upon r square. Now, if we want electric field on the surface of sphere itself, means we are talking about the surface, means on the surface of this sphere, then E on surface, we'll write like this, E on surface will be equal to kq upon, what is the distance? The distance is the radius of the sphere itself, it is capital R, so q upon capital R square. E outside is kq upon small r square. For outside, you have to take care to write small r square. For on surface, you have to write capital R square, because capital R is the radius of the sphere and small r is the radius of the Gaussian surface. Now, the third one. Have you understood this? Now, the third one will be, if charge resides on outer surface, then charge inside the Gaussian surface is 0. Means, if this is the condition that the charge is always on the surface of the sphere, then if we want the electric field intensity inside this means inside this sphere, then it is always 0. How it is 0? I am going to tell. We know that phi is equal to, flux phi is equal to E integral sign dA. We all know this. And what is phi? According to Gauss law, phi is the q net, means net charge upon epsilon naught. And what is the area? What is the surface area of the sphere? Remember the formula of maths? It is 4 pi radius square. What is the radius? Radius is capital R. So 4 pi r square. Suppose this is first equation. Q net upon epsilon naught is equal to E 4 pi r square. But here we know that Q net is equal to 0. Charge inside the conductor is 0. So in place of Q net in equation 1, we can write 0. So it is 0 upon epsilon naught is equal to E into 4 pi r square. It is very clear that due to this charge net equal to 0, the electric field intensity will always be 0. So electric field inside the charged sphere, this is electric field inside the charged sphere. is always 0, and the reason is Q net equal to 0. Now, very important graph between E versus R. So graph of E versus R can be drawn. Suppose E is taken on y-axis and R on x-axis. I explained you in my previous video also, but again I am explaining here. Suppose if we talk about the electric field intensity inside the sphere. So inside the sphere, the electric field intensity is 0. This is represented by this line overlapping the x-axis. So this shows E inside. This shows this E equal to 0. Now, if we draw the curve like this, then this curve shows E is inversely proportional to R square, and this is for outside, and this E is maximum at outer surface of sphere. E is maximum at outer surface of sphere. Why this E is maximum at outer surface? Because this R, capital R, is less than small r. So if denominator is less, because it is inversely proportional to capital R square, if denominator is less, then E will be more. So among all these three, the electric field intensity is outside the sphere, inside the sphere, and on the surface of the sphere. The electric field on the surface of the sphere is maximum. Inside the sphere it is 0, and outside the sphere will depend on this formula. E is equal to KQ upon R square, where R is more as small r is more as compared to capital R. So if this will be more, then electric field intensity will be less. And as we move away from the charged sphere, the R will be increased. R will go on increasing mode. So it will be increased. As it increases, the electric field intensity always decreases, because they are inversely proportional. If small r will increase, then according to that ratio, this capital E, electric field intensity, goes on decreasing. So this graph shows the decrement of the electric field intensity. It goes on decreasing due to the increment in small r. Okay, thank you.